Okay, we will go through some important points in the class 12 physics chapter 12 atoms. Okay, this is the J.J. Thomson's model of the atom. According to this model, the positive charge of an atom is uniformly distributed through the volume of the atom, and the negatively charged electrons are embedded in like seeds in the watermelon. Okay, so the positively charge is uniformly distributed and the electrons are embedded like seeds in a watermelon. It is called plum pudding model. Okay, so what is the drawback of this model? Hmm, as described, it shows that in the later studies, it shows that the distribution of the electrons and positive charges are very different from the proposed model. Okay, so the later on it found that the distribution of electron and positive charges are different from this proposal. Okay, it is also found that they emit electromagnetic radiation. Okay, so he could not explain that functions. Now this is the Rutherford's model of the atom. Okay, according to this, the entire positive charge and most of this mass of the atom is concentrated in a small volume called nucleus. Okay, most of the mass is in the nucleus with the electrons revolving around the nucleus just as planets revolve around the sun. Okay, planets revolve around the sun like that, the electrons revolving around the nucleus. That is what Rutherford found, but he could not explain why atoms emit the light. Okay, again he could not explain why the atoms are emitting the light at different discrete wavelengths. That is the limitation of the Rutherford model. Okay, this is the alpha particle scattering experiment. So this is the zinc sulfide screen, this is the gold foil, and the alpha particle is passed through this narrow hole, and it is strike on the gold foil. Some particles get scattered, and with so different these are the different angles that the particle gets, alpha particles getting scattered. Okay, zinc sulfide screen, this is the scattering angle. Okay, instead of straight, these are the scattered alpha particles. So large angle of deflection here, large angle of scattering. This is the backward scattering, that is a very small amount. This is small angle. These are how many particles deflected by 1 degree, 90 degree they have given the data. So this is a graph of the angle and the scattering angle and the number of particles. Okay, you see less number of particles are getting scattered at the larger angle, that is around 180 degree. Less number of particles getting scattered, so that is the near the nucleus. Okay, then near when the particles bombarded at the nucleus scattered at higher angles. Okay, than the other places. See, the here deviation is less angle, here more number of particles get scattered angle less, few less number of particles are scattered at the larger angles. So that is the near the nucleus. So the size of the nucleus and the size of the atom here given. Okay, the atom is approximately this size, this is the nucleus size. So that means the electrons would be seen at a distance of from the nucleus about 10,000 to 1 lakh times. Okay, from the nucleus, if you compare the distance of the nucleus with the atom, this much times is the distance. Okay, that means most of the atoms are empty, only the nucleus at the center and the electrons far away from it. The what is alpha particle is nothing but the helium atoms, therefore it has 2 units, 2e alpha particles. The gold is around 50 times heavier than the alpha particle. Okay, that is why it's getting deflected, because the gold foil, we are using the gold foil in the experiment. Okay, gold foil, and that is 50 times heavier than the this alpha particle. That is why it is getting deflected. So, okay. So this is the alpha particle, and the gold, this is the force. Alpha particle trajectory, this is the deflection angle, and the alpha particle. They are computing something called impact parameter. Okay. Impact parameter is minimum, and the alpha particle rebounds at this angle. For the larger impact parameters around 0. So the most of the mass is concentrated on the smaller volume. Okay. In the Rutherford nuclear model of the atoms, the nucleus is around 10 power minus 15 meter, is analog to the, if you make it analogous to the sun and the planet, sun about which the electrons move in the orbit. Okay, this is the nucleus, like Earth orbits around the sun. If the dimension of the solar system had the same proportional to the atom, like the solar system also, sun like nucleus and the earth like electron, they are comparing. Okay, would the earth be closer or far away from the sun? If you make the comparison same as the atom, so will the earth be closer to the sun or far away from than the actually it is now? The radius of the earth they are given. Okay, radius of the sun. Okay, the radius of the electrons orbit and the radius of the nucleus is 10 power. This is the nucleus and the orbit of the electron. That is, the radius of the electrons orbit is 10 power 5 times 10,000 to 1 lakh times larger than the radius of the nucleus. If the radius of the earth orbit around the sun, where 10 power, if earth is 10 power 5 times larger than the radius of the sun, that is the assumption, the radius of the earth orbit would be this much. Okay, this is more than 100 times greater than the actual orbital radius of the earth. Okay, more than 100 times the actual radius of the earth now. Thus the earth would be much farther away from the sun. Okay, if we make the same assumption like in nucleus and electrons in the atom, same assumption we make for the sun and earth, then earth would be much farther away from the sun. It implies that atoms contain a much greater fraction of the empty space than our solar system. This experiment, what is the distance to the closest approach to the nucleus of 7.7 mega electron volts alpha particle before it comes momentarily at rest and reverses is the direction. The key idea here is throughout the scattering process, the total mechanical energy of system consisting of the alpha particle and the gold nuclei is conserved. Okay, the energy is conserved. The system's initial mechanical energy is E before the particle and the nucleus interact. It is equal to the mechanical energy when the outer particle momentarily stops. The initial energy is just the kinetic energy of the incoming alpha particle. The final energy is just the electrical potential energy. Okay, kinetic energy and electrical potential energy you can be calculated from okay. So now this is the kinetic energy and the potential energy. The maximum kinetic energy found in alpha particle is okay. So this is and all is using directly equations. Okay, the radius of the gold nucleus is therefore less than this is not the very good agreement with the observed result, and the actual radius of the gold nucleus is 6. Okay, thus the alpha particle reverses the motion without ever actually touching the gold nucleus. Electron orbits electrostatic force Fe and the centrifugal force Fc. This is a centrifugal force, this is electrostatic force. This is the relation between the orbit and its velocity. Okay. So this is for the hydrogen atom. You see, the total energy is just is the sum of the kinetic energy and potential energy. So this total energy is negative of the kinetic energy. You see, this is the kinetic energy and total energy is just negative of this energy. Okay, total energy is the negative of the kinetic energy, and the kinetic energy is half of the potential energy. This is the potential energy, this is the kinetic energy, is just half of this uh, potential energy is the kinetic energy. Otherwise potential energy is twice the kinetic energy. So it is found experimentally that 13.6 electron volt energy is required to separate a hydrogen atom into a proton and the electron. Compute the orbital radius and the velocity of the electron in the hydrogen atom. Total energy given. Okay, so that is converting electron volt into joules. So 1.6 in 10 power minus 19 joules is 1 electron volt. Okay, so this is the energy, they are given the energy. Okay, this gives the orbital radius. So the velocity, these formulas are given above, you can go through those formulas. Okay, this is the various series wavelength, and series name, Lyman series. This is given in nanometers. Okay, nanometer, 10 power minus 9 meter. According to the classical electromagnetic theory, calculate the initial frequency of the light emitted by the electron revolving around a proton in the hydrogen atom. Okay, this is how the frequency and the velocity is related. Okay, frequency of the electrons around the moving around the proton. Okay, this is the frequency, velocity by 2 pi or radius of the orbit. Okay, this is the frequency and velocity relation. So these are the three Bohr's modified is modeled into the three postulates. So he says in this first there are defined state in which electron definite stable state in which these are called the stationary states of the atoms, and such possible state has a definite total energy. Okay, each atom has a certain definite stable state in which it can exist, and each possible state has a definite total energy. Okay, that is first. The second, the orbits for which the angular momentum is some integral multiples of the h by 2 pi. H is the Planck's constant. Okay, the angular momentum is integral multiple, that is n into h by 2 pi. N is nothing but the quantum number, principal quantum number. Third postulate, okay, says the difference in energy is this Planck's constant in the frequency. Okay, this is the radius of the nth possible orbit. Actually it is not clear here, so here you go to 14. See here h by 2 pi square they have to put, right? The bracket is not there. So see here they have put bracket clearly. Okay, in this formula, radius of the earth, radius of the orbit. Okay, this is the negative sign. The total energy of the electron moving in an orbit means that electron is bound with the nucleus. These are the energy levels. This is the ground state. These are excited state. That is after observing some energy it goes up. Ground state. What is ionization energy? Okay, the minimum energy required to free the electron from the ground state. Okay, this is important. From this ground state you have to free the electron. The hydrogen is called the ionization energy of the hydrogen atom. Minimum energy required to get the electron free from the ground state. Difference in energy is equal to this Planck's constant in the frequency. De Broglie explanation of the Bohr's second postulate of quantization. 2 pi r equal to this energy. Lambda equal to h pi p. P is the momentum of the electrons, magnet of the electrons momentum. So this angular momentum mvr equal to nh by 2 pi. Okay, this is the radius of the orbit formula, energy on that orbit. Okay, exercise. Choose the correct alternative from the clues given at the end of the each statement. The size of the atom in Thomson's model is no different from the atomic size of the Rutherford model. Okay, the Thomson model and Rutherford model, they are not differing in terms of the size of the atom. They differ only in terms of how the nucleus and electrons are distributed. Okay, so this is no different. Okay, the size of the atom in Thomson's model is no different from the atomic size of the Rutherford's model. Okay, they are talking about the size of the atoms whole. In the ground state of the Thomson's electrons are in stable equilibrium, which in Rutherford's electrons always experience a net force. Okay, the Rutherford's nucleus is positively charged and negatively charged electrons revolving around the nucleus. So in the ground state of the Thomson's electrons are in a stable equilibrium, while in Rutherford electrons are always experience a net force. The classical atom based on Rutherford's is doomed because it doesn't explain the emission of the electromagnetic radiation. An atom has a nearly continuous mass distribution, that is as per Thomson's model, but it is highly non-uniform mass distribution as per the Rutherford's model. Rutherford says most of the mass is concentrated at the center of the atom, that is a nucleus. So that is the non-uniform mass distribution. But in Thomson's model is a nearly uniform distribution, continuous mass distribution. The positively charged part of the atom possesses most of the mass. Okay, in both the both the models means which one the other model, Rutherford model and what is the other model is. So both the models, positively charged part of the atom possesses most of the mass. Suppose you are given a chance to repeat the alpha particle scattering experiment, but making a thin sheet of the solid hydrogen in place of the gold foil. So the hydrogen, so here the gold foil is around 50 times heavier than the alpha particle. Okay, that case. But in this case, the alpha particle is 4 times heavier than the hydrogen, so it will not deflect, scatter. Okay. See, the mass of the hydrogen is this many kg, 1.67, but mass of the alpha particle, that is helium atoms, to 6.4 in 10 power, so it is around 4 times the heavier than the hydrogen, so it will not get, so not scattering. Okay, here see, in the original alpha particle scattering equipment we are using gold foil, and the alpha particle is made to collide. Okay, that alpha particle is lighter than the gold foil. See, here in the original gold is 50 times heavier than the alpha particle. Okay, that is why scattering takes place. A difference of 2.3 electron volts separates two energy levels in an atom. Okay, final and the initial energy difference they have given. What is the frequency of the radiation emitted when an atom makes a transition from the upper level to the lower level? Okay, difference in energy equal to HV. They are asking what is the frequency of the radiation. Okay, the difference in energy they are given, initial minus final. So from that, frequency is equal to energy divided by Planck's constant. Okay, energy in the initial state, final state, Planck's constant, 1 electron volt equal to 1.6 into 10 power minus 19 joules. Okay, if we substitute, then you will get the frequency in hertz. Okay. Difference in energy level equal to Planck's constant, the frequency. Okay, this is the frequency of the emitted photon. The ground state energy of the hydrogen atom is given. What are the kinetic and potential energy of the electron in this state? Okay, the ground state. Total energy equal to kinetic energy plus the potential energy. Kinetic energy is this, I will show you in the book. This is the potential energy. So the total energy is just a negative of the kinetic energy. This is the total energy. Kinetic energy is the negative of the total energy. Potential energy is 2 times the kinetic energy. Okay, so using this you can find out the kinetic, what is kinetic energy, what is potential energy. See, they given here total energy equal to kinetic energy, potential and plus potential energy for the hydrogen atom. Okay, using this formula you compute that. A hydrogen atom initially in the ground state absorbs a photon which excites into the n equal to 4. Ground state is n equal to 1. Okay, n equal to 4. Determine the wavelength and frequency of the photon. Okay. So n equal to 1 equal to 13.6 electron volt. Okay, the lambda equal to the difference in energy. Okay, difference in energy, energy at a particular state is n equal to 4 means 4 square 16. Okay, and I will show you the formula in the book. So now using this, so lambda, this is the difference in energy. This is the nanometer. Okay, if you then from the lambda you use this formula to find out the frequency. 3.1 in 10 power 15 hertz. See here, energy at the nth level is 13.6 by n square. Okay, and this is the formula we are using. Using the Bohr's model, calculate the speed of the electron and the hydrogen atom at this level. Okay, calculate the orbital period also. Okay, this formula is given in the book. Okay, using the Bohr's formula, that angular momentum MUR equal to NH by 2 pi. For n equal to 1, this is the frequency. Okay, from that we are computing the frequency. For n equal to 2, sorry, this is the velocity of the orbit. The first orbit, this is second orbit, this is third orbit. We have to substitute the value of the n. Here this NH. So now we have to use the frequency equal to velocity by 2 pi r. Frequency is equal to 1 by t. So find the period equal to 2 pi r by v. Okay, this is the velocity. Now this formula is given in the book, that radius. Okay, 2 pi r by v. For the r I am substituting formula from the book. After substitution this will become like this. Then you compute the period. 2 pi r, instead of r you are using that formula, then this will become the, you will get this answer. The radius of the innermost electron of the hydrogen is given. What are the radii? Okay, the innermost n equal to 1 is given. For the other n equal to 3, they are asking what is the radius of that orbital radius. See, the orbital radius in this, the only variable is n. This is the quantum number. Okay, all the other thing is not based on the orbit. Okay, all the other things are constant. Okay, h, these things, l, m, everything is constant, only this varies. So Rn is equal to n square into r1. R1 means 1 square, this constant. Okay, so this is the formula we will be using. So this is the formula, in this only n is the variable. Okay, so we take out n, the remaining, this is a constant. So Rn equal to n square into r1. So using that you can find the what is the radius of the other orbits. Okay, this is the radius of the first. From that you substitute, only variable is this. Okay, 12.5 electron volt electron beam is used to bombard gaseous hydrogen at the room temperature. What is the series of wavelength? E equal energy equal to Planck's constant in the frequency, hc by lambda. So this one, if you substitute, you will get this. So in the Lyman series, this is given in details, given for this in the class 11 chemistry atomic structures book. So in that you use n1 and n2. This is for the shorter wavelength. N1 is equal to 1, n2 equal to infinity, you take, you will get this. Similarly for the long wavelength, you will n1 equal to 1, n2 equal to 2. The next thing you will take this. So this is in Armstrong unit. So then this wavelength is lies in between this shorter and the longer. This is lies in the region of the Lyman series. Okay. Okay, that is given in the class 11 chemistry book. See here, this series, it is given in nanometer. Our computation came in the Armstrong 10 nanometer 10 Armstrong is equal 1 nanometer. Okay, so that our computation results came within this band Lyman series. In accordance with the Bose model, the quantum number that characterizes the Earth's revolution around the Sun in an orbit of radius is given with the speed velocity is given. Okay, so we have to find the quantum number. This is the angular momentum L equal to nh by 2 pi mvr. From that n quantum number equal to this is the formula. After substituting you will get this quantum number. L equal to nh by 2 pi, that is L equal to mvr. So substitute that and you will find the quantum number. Okay.